hi everyone. Thanks for coming. We have a presenter from our own crew today from CBCS here doing his PhD here at UQ. This is Lenn, originally from the other St. Lucia in the Caribbean, the real St. Lucia, I think.
Yeah, St. Lucia, yeah.
But he is based at our St. Lucia and doing a bunch of cool stuff with acoustic monitoring and how to, I guess, make it better and feasible and design it and actually use it. Lenn has actually done real work in the real world with monitoring and conservation and management. Lenn, was that mostly in the Caribbean or?
In the Caribbean, yeah. Yeah. St. Lucia and a few other islands.
And is your PhD research kind of focused on the Caribbean, or is it?
No, primarily focused on Australian species, but I mean, broad application. So
yeah,
I can take it back home whenever I go back.
Yeah. Cool. Well, yeah, it'll be cool to hear some about this new tool and from someone who's actually has some experience in different places using it and trying to manage and monitor species. So I should probably say the title of your talk. What is the title of your talk? I've lost the email.
Does acoustic monitoring make sense?
Yes, there we go. I remembered it was a good title. Okay. I will hand it over to you, Lenn. Thanks.
Cool. Thanks, Leslie. Okay, let me just share my screen. And then go full. Can everybody see? Yeah, all good?
I think we're good.
All right. So thanks again for the introduction, Leslie. Good morning, everyone. So I'll be presenting a part of my PhD project, one particular chapter. And as I just said, the title is, Does Acoustic Monitoring Make Sense? But first off, what exactly do I mean by acoustic monitoring? I'm referring to the use of these devices, so unattended sound recorders. Now, over the past decade or so, these types of recorders have been gaining traction as wildlife monitoring tools. Question is why? Like, what's so special about these devices? Well, consider these two species. So here on the left, you have the eastern ground parrot, and on the right, you have Lewin's rail. So I've done a number of ground parrot surveys, and on some occasions, on many occasions, in fact, I'd hear the birds calling all around me, but would not see a single individual. I can also remember one time I was out birding, I was trying to see a Lewin's rail. I could hear the bird, it was less than 3 meters away. And I stood for 2 hours like a statue, just waiting to get one glimpse. And there are lots of other examples which are of species, which are extremely difficult to see, but can be easily heard. And thankfully, with these devices, instead of visiting your field site for many hours, day after day, hoping to see or hear your targeted species, you can simply leave one of these recorders at your site and return to collect the audio data in the coming weeks or even months. But are these devices as effective at detecting vocal wildlife species as other monitoring methods? Well, there have been a handful of studies investigating these sorts of comparisons, but the results have been mixed. So whether it is to detect a particular species or to determine species richness, in some instances, the sound recorders prove to be more accurate or more effective at detecting the species of interest. And in other cases, the non-acoustic methods were more accurate. And this is where my project comes in. So we decided to take a closer look at this issue of comparing acoustic monitoring to other methods. But unlike previous studies, which primarily compared the accuracy of the methods, we wanted to use a metric that combined accuracy, costs, and some of the relevant variables. We used a cost effectiveness formula borrowed from this paper at the bottom of the screen. The A in the formula represents the accuracy of the monitoring method, and to determine accuracy, we accounted for two probabilities. So first up, the probability of correctly detecting the species when it is present, that's a true positive. And then we also accounted for the probability of incorrectly detecting the species when it is in fact absent, the false positive. The R in this formula represents the probability that the monitoring method poses some sort of risk to the species or its habitat. For instance, there might be a risk of disturbing or stressing the species, maybe damaging the habitat, sorry. F represents the feasibility, which is the probability that the needed data can be successfully collected. But also includes the probability that the monitoring program will actually be implemented. And the C, of course, represents the cost in dollars. Now, for each of these species, there are several methods which can be used to monitor any one of them, including acoustic methods. And from the left to right, we have the Wallam froglet, tiny acid frog found in Southeast Queensland. You have the koala, of course. You have the night parrot, the plains wanderer, and the glossy black cockatoo. So we use these as case studies to compare, along with a few other species. But we use these as case studies to compare acoustic monitoring methods to other techniques using the cost effectiveness formula that I just referred to. The only challenge was that we had little to no data on accuracy, risk, or feasibility of the methods in question. So what were our options? How could we work around this lack of data, this data limitation? Well, structured expert elicitation is an option. In situations where you don't have enough data to make decisions, structured expert elicitation allows us to use the educated guesses of experts to fill in the gaps. And how does this process work? Well, you get relevant experts together in a workshop setting and ask them to estimate the values of certain variables of interest. Now, there are certain sources of bias to consider when getting the opinions of experts, particularly in a group setting. For example, you have groupthink, you have overconfidence, you could have the dominance of one particular individual. But structured expert elicitation allows us to minimize these sources of bias. So for each of these species, we recruited a team of experts and we held a series of workshops, both in person and remote, to conduct the expert elicitation process. And we take a closer look at this process now by focusing on one of our case studies. And by the way, the expert elicitation method we use is based on the paper at the bottom right here, a practical guide to structured expert elicitation using the IDEA protocol. So we recruited a team of koala experts, and they were interested in comparing the use of detection dogs to acoustics. Detection dogs are used to detect koala cats, or in some cases, the actual koala individuals. And at the workshop, we first asked the experts to define the main objective of the monitoring program. Then we asked them to define two hypothetical but realistic monitoring scenarios. One scenario was simple, and that involved monitoring over a very small area. That is the smallest area that they would realistically want to monitor, small in the context of koala monitoring. And the second scenario was complex, and that involved monitoring over a fairly large area. And all monitoring was to be conducted over a 12-month period, 1 year monitoring. So here we have the objective of the koala study, presence absence at the site or sites. Simple scenario, relatively small in the context of koala monitoring, 1,000 hectares. And the complex scenario, much larger area, 1,000 square kilometers. Then we asked the experts to define the risks posed by monitoring. So they came up with these two. Monitoring may increase koala deaths, and monitoring may increase koala stress. And next off, the experts, we asked them to discuss the details of the costing details of the monitoring methods. The approach to costing that we use is based on this paper, standardized reporting, of course, of the cost of management interventions for biodiversity conservation. And costing considerations included one-off purchases such as equipment, as well as recurring costs such as labor, and consumables such as batteries, food, and fuel. And the experts estimated these costs for both methods, detection dog and acoustics. Once the costing was complete, they estimated the other variables needed for our cost effectiveness equation, the accuracy, the risk, and the feasibility. For the accuracy, we asked the experts to individually estimate the true positive, then estimate the false positive. And all this was done in 3 steps. Step 1, each expert individually provided the lowest possible estimate of a true positive. Then they provided the highest plausible estimate of a true positive, then the very best estimate. And they also provided the confidence. And the confidence is the likelihood that the actual probability of a true positive lies between the lowest and highest estimates that they had provided. It might sound a bit confusing here, but happy to answer any questions after or recap. The same was done for the question concerning the false positive. Step 2, each expert submitted the estimates to the workshop facilitator. Then the workshop facilitator anonymized these estimates and then presented them to the entire group for discussion. The group of experts discussed possible reasons for differences in the estimates, and they clarified any uncertainties or ambiguities. The experts then split up again and repeated step 1. The same process was then repeated for the 2 remaining variables for our cost effectiveness equation, the feasibility and the risk. Now, what did you find? So the blue bars represent the detection dog, the red ones represent acoustic monitoring, and not much difference between the accuracy estimates of the 2 methods. And we found basically the same thing for the risk and feasibility. So accuracy, risk, and feasibility were very similar between the methods. But for the costs, we found serious differences. So the startup costs were much higher with the acoustic approach, which is not surprising. But if the recurring costs, we have a stark difference with the simple scenario and not much of a difference with the complex scenario. Now, what does all this mean in terms of cost effectiveness? So remember, we asked the experts to base the estimates on 12 months of monitoring, but we then extrapolated to 5 years. Focus on the solid lines. So the red line represents acoustics, the blue line represents the dog, detection dog. And we can see that if we monitor for only 1 year, only for 12 months, the dog is clearly the most cost-effective method. If you monitor for 2 years or more, then acoustics is a better option. And this is with the simple scenario, 1,000 hectares, relatively small area. With the complex scenario, much larger area, the detection dog was more cost-effective throughout. Although at 4 years and beyond, there really isn't much difference between the methods. Now let's look at another one of the case studies, the one on froglet, one of the tiny acid frogs. The comparison here is between acoustics and oral surveys. By oral surveys, we simply mean humans listening. So the way these frogs are monitored, you typically wait for a rainfall event and you go out at night and you listen for the frogs. So that's what oral surveys are. And on the left, we can see over a small area, there was not much difference between the 2 methods. The oral surveys are just slightly more cost-effective throughout. Over a large area, oral surveys are much more cost-effective than the acoustic monitoring option, whether monitoring for 1 year or for 5, it didn't matter. Another case study, the glossy black cockatoos. So the objective here was a bit different. So we're trying to detect whether or not there had been any fledging events at the site. Here we see monitoring across a small area. If monitoring for less than 3 years, looking at the graph on the left, if monitoring for less than 3 years, observers are more cost effective. But beyond that, acoustic monitoring is a better approach. And over a large area, now we're looking at 200 square kilometers, the graph on the right, acoustic monitoring is more cost effective throughout. So here we have an overview of the results that I just showed, and you can see the graphs side by side. You can see the differences in the results. So it's apparent that we cannot predict when acoustic monitoring is preferable from a cost effectiveness standpoint. Its relative cost effectiveness varies according to the temporal and spatial scales involved and the specific details of the monitoring program. But the process that we use can be adopted by researchers to help them select the most cost-effective strategy for a given scenario. The framework that we're proposing can be used with a broad range of objectives. Various metrics for accuracy can be used in the cost effectiveness formula, and different types of risks can be included. What we offer is a simple, repeatable, and flexible strategy for making decisions concerning monitoring. Thank you. And special thanks to CBCS for funding the in-person workshop, for my dear supervisors, and special thanks to all the workshop participants. Any questions?